Right. Welcome everyone to this Monash Cybersecurity Seminar. Today we are happy to welcome Xiao Wang, who is an assistant professor at Northwestern University. Xiao Wang's research interests include computer security, privacy, and cryptography. And recently he has been working on practical multiparty computation, zero-knowledge proofs, oblivious RAM, and post-quantum cryptography. And he likes building real systems based on advanced cryptographic techniques and pushing their limits to the practicality. And today, Xiao will talk to us about efficient and affordable zero-knowledge proofs, ResNet, Inference, and RAM computation. Thank you very much, Xiao. The scene is yours.
Thanks. Yes, today, so I'm going to talk about zero-knowledge proofs with a particular set of features. So the first is that it is efficient and affordable. And the second is that we can actually, it's not very hard to build different kind of applications on top of that. So I'm Xiao from Northwestern University, and so the whole presentation is based on multiple papers, and thanks to all the co-authors that has been contributed a lot on the project. So for zero-knowledge proof, so the definition, like I suppose like many of you already know like what it is. So essentially, so we have a prover who has a witness, and the zero-knowledge proof protocol can be viewed as an ideal functionality that that verifies like some predicate of the input X, for example, where the predicate can be defined in, for example, as a circuit or as any kind of like program, and tell the verifier that okay, so actually the predicate is satisfied. Okay, so they have like for example, depending on how it is formalized, there are different kind of ways to formalize it, to formalize its security. Okay, so I don't want to go into the details of the definition, but there are many different kinds of popular approaches in terms of define how to construct a zero-knowledge proof. For example, we can there are different kind of like ZK snarks. There are like IOP-based protocols, like there are like GKR protocols and like MPC in the head, and also for example zero-knowledge proofs from Gobble circuit. Okay. So I mean this is just a very like incomplete list of constructions that can be used to construct zero-knowledge protocols, and the last one is very different from the previous ones, because for the first four they can all be made non-interactive, while the last one cannot be made in non-interactive because of some restrictions about this protocol. Okay. So that's this is just more about the approaches how to build zero-knowledge proof. Okay, and if we look at how the proof the features, actually we can think about it in another dimension. Okay, so the first one is what I just mentioned, that some of the protocols can be made non-interactive, while others are inherently interactive. So why non-interactive is nice? For example, let's say if a protocol is non-interactive, then the proof can be forwarded to some other verifier without doing recomputing, and it's also better, for example, when the network latency is higher. So non-interactive have some benefits compared to interactive. And in terms of the proof size, okay, so there are also, for example, some succinct, somewhat succinct, and not succinct at all. So, okay, so usually not succinct at all means that the proof size is linear to the circuit size. Okay, and somewhat succinct, for example, could be where the proof size is kind of for example square root of the circuit size, likely Harrow. Okay. And the succinct usually for example it can be like a polylog of the of the circuit size. So these two first two bullets are have been the main focus for most of the works in zero-knowledge proofs. Okay, and then the next part is somewhat studied, and but they are not so in many cases they are these are the trade-offs that we are willing to pay. For example, the first one is going to be the computational efficiency. Okay, and here in terms of the computational efficiency, we can also roughly kind of characterize it into few few levels. For example, the heaviest one would be, for example, for each gate we need to do a constant number of public key operations or exponentiations. And then the next one would be, for example, we needed to do some kind of, let's say, number theoretical transformation on the whole circuit. This is kind of slower because we would need let's say, given a circuit of size C, we would need C log of size C number of like arithmetic computation. So it's not linear. Okay. And then the last one would be, for example, we just need to do a constant number of symmetric key operations that can hopefully, for example, be very, very fast. Okay. So here, like I'm kind of so if we want to do anything better than like a constant number of symmetric key operations per gate, then it will be very challenging because like given the modern hardware, like symmetric key operations and like normal arithmetic computations, they are like the gap between them is not very high. Okay, and then the next dimension would be like a trusted setup. Okay, so whether we need a trusted setup and whether this kind of setup is universal for any kind of statement, or the setup is actually like it's kind of different for different kind of statement that we want to prove. Okay, so all four of them, this like the top four bullets are kind of the normal ones that we usually think about when we talk about zero-knowledge proof. However, the last one has rarely been studied since until recently. That is the memory requirement for a zero-knowledge proof protocol. So for example, so this like it might be unclear why we want to discuss it at all, because like the memory requirement is probably going to be something like the circuit size, but that may not always be the case, and it is obviously far from optimal, because let's say if you have a circuit, to evaluate the circuit in the clear, it could be very like the memory requirement of that can be very small. Could be constant if the circuit is has some particular shape. And it could be, for example, like can often be, for example, logarithmic of the size of the circuit. But in many existing protocols, actually the memory requirement is like a linear. Then this would mean a exponential gap between what we can do in clear text and what we need in, like when we add crypto on top of it. Yes, and the attention that is paid on the upper part is like much more than the attention that has been paid for the bottom, for the lower parts. So this actually actually means a lot in terms of the scalability, because like for example, let's say if we wanted to make zero-knowledge proofs affordable and scalable, that memory requirement is definitely going to be a very big factor in terms when we get into the real implementations. Because let's say if a circuit of size 1 billion gate would need some memory that is proportional to 1 billion, then going beyond 1 billion is going to be very difficult because of the memory requirement. Okay, and so if you look at the settings, so the reason that for example non-interactive ones have been studied a lot more than interactive ones is because for most of the settings, we are kind of assuming that we have a zero-knowledge, we have a prover, and the prover would like to prove about a statement to multiple verifiers. And for example, the prover could send can kind of broadcast the proof to all the verifiers, and all of them can kind of verify them like offline or in parallel. However, there's also another kind of setting, like in terms of zero-knowledge proofs, that can also be like very useful in practice. That is a more kind of a synchronous setting, where the prover wants to prove to a verifier, and the verifier can stay online with the prover, so that they can, for example, do some kind of interactions between them. Okay, and so the first setting, so protocols that could work for first setting but not a second setting, is not really very studied. For example, like the zero-knowledge Garble circuit protocol would be like that because it's like interactive. And in this work, we will be mostly focused on kind of a synchronous setting where the verifier can actually come online and talk to the prover while they do some computation. So this is obviously a kind of a restriction in terms of the applicability of our protocol. But on the other hand, we can actually achieve a lot more properties on other stuff. So our protocol is interactive, and actually it's often the proof size is often linear to the size of the circuit. Okay, that's the first two parts. That is like the downside of our protocol. Okay. On the other hand, the benefit of our protocol is that first, it's very computationally efficient. So in order to compute a circuit in order to compute any circuit, we just need to do a constant number of AES plus constant number of a field operation on top of some kind of extension field per gate. And both of them, fortunately, can be accelerated on like a modern CPU. So like everybody's computer can actually do these two operations efficiently. Okay. And in terms of the memory, so our protocol is actually only needs memory that is linear in terms of what it would be needed when we evaluate the circuit in the clear. So so this is actually much better in terms of the memory consumption compared with many of the existing work. And finally, the protocol does not need a trusted setup and is UC secure. So this is not very surprising because so we already allow interaction. So many of the impossibilities can actually be avoided easily. So the last one is not really anything surprising. However, the efficiency and the memory is really the advantage of our protocol. Okay. And yeah, so I kind of claiming that this is almost what you can the best that you could hope for, given the modern ways of how the computer works and what are the operations that can be supported. Because even with the information theoretic protocol that just needs a constant number of arithmetic operation, it's not going to be too far away from what we can do right now. And this will be clear when we get into the performance numbers in the end. Okay. Okay, so in terms of the technique, so I listed the 3 bullet over here, but there's actually a bullet 0 at the top. Okay, so the bullet 0 at the top is the existing work done by many great researchers on fluid random correlation generators. Okay, so this really laid the groundwork of in terms of how to kind of construct this kind of interactive commitment, which we call authentication on the wires in the circuit. Okay. So once we have this is kind of the first part, and then the second part would be how to check that the circuit can be computed correctly. And here we actually the first part we actually talk about this in one of our papers in CCS 2020 that I'm not going to talk about in this talk. The name of the paper is called Ferret, which is this animal. Okay, very cute. So I will focus on the second part and the third part. And the second part, there's so the second part is going to be about how to check the circuit, and here so we actually I'm going to talk about the Wolverine, which is our first paper on in terms of how to do the checking. This Wolverine check is actually incurs a linear communication cost, but it's kind of very intuitive why we are doing it this way. Okay, and afterwards, we have a follow-up paper called Quicksilver, and over there we kind of extend the ways of the Wolverine check, based on some other prior work, and also extend it to with further flexibilities. Okay, and after this two, I'm going to talk about 2 applications using this kind of circuit-based zero knowledge, how to build, for example, zero knowledge proof of machine learning inference, and how to build a random computation on top of our zero knowledge proofs. And if you have any questions, feel free to put it in the chat or Q&A. I'm able to see them immediately. Okay, so so as some kind of a background, I need to first talk about information theoretic authentication code. Okay, so this concept was originally proposed roughly it's certainly more than 10 years. I think roughly 20 years ago, when when people were trying to design a secure multi-party computation protocols with maliciously secure MPC with where the adversary can corrupt all but one protocols. Okay, and the 2 very famous ones is Bedoza and the Speeds. Okay, so the difference between Bedoza and the Speeds is how they use the authentication code, but how they are organized. But both of them use this information theoretic message authentication code, and this is was actually firstly proposed in Bedoza to use as in secure computation protocols. Okay, so in this kind of protocol, in this kind of code, so essentially so we have prover and verifier, and the verifier has a global delta. This global delta is kind of a unique value that is just held by the verifier that is not going to be changed. Okay, and so this kind of authentication gives prover a MAC M sub x and give the verifier a key K sub x. But these are not just arbitrary values. They hold a specific correlation that this MAC is computed as the key plus the multiplication of the value that is being authenticated times the global key. Okay, so this kind of correlation allows so let's say if the prover and the verifier hold like some kind of relationship like this, then the prover later cannot really cheat, cannot kind of lie to the verifier that actually the value is something else, because in order for the prover to kind of convince the verifier that this value was some other commitment, then like the prover has to actually be able to guess the value of delta correctly. Okay, and you can see why this is very important in like multi-party computation, because this is essentially a way for the parties to commit to some kind of a computation and be able to kind of open them in like later without using a real commitment, because this is like much more efficient. Another thing that is very nice about this kind of information theoretic authentication code is that it's also linear. So it's linear in the sense that so I'm going to use this kind of bracket notation to denote the authentication of a value that is held by the prover. So prover hold this value x, and also the MAC, and the verifier hold kx. I'm going to use bracket x to represent this kind of the values and the distributions of the values associated with x. Okay, and if the two parties hold the authentication value of x and x prime, then it's actually it's actually obvious that actually we can compute there's a way to easily compute the summation of the authentication of the summation of the two values, which is so this can be done essentially by everyone just summing up their own local values, and this x prime prime is a bracket is going to be the authentication of x plus x prime. Okay. So this is we can do addition homomorphically. We can also do addition by a constant in a similar way, and multiplication by a constant is also supported. So this kind of authentication code is very nice because of this kind of homomorphism. Okay. So one thing that I didn't mention is that the opening of this kind of value is also almost for free. So so to open a value from the prover to the verifier, the communication is literally just sending the value of x. Okay, so and there is if we don't want to send x, the communication is still very small. So there are ways to kind of, for example, checking whether our authenticated value is 0, also with almost no communication cost, and with a very cheap computation. And in terms of being the ways to compute this kind of value, so in our work, the ferret work that I'm not going to talk about it over here, actually this kind of thing can be done very, very efficiently. Let's say if we want to authenticate a bit, then every authentication can be computed using just 14 nanosecond for each of the authentication bits. So literally this is almost for free if we think about it, because any other operation that we want to do on top of it is probably going to be on the order similar to 14 nanosecond. So this kind of authentication is really, really not very expensive. So we can kind of feel them almost for free in some sense. Okay, and even if we want to do some kind of authentication on over a larger field, the communication is also the computation is also not very expensive. Actually, this number is actually outdated already. I think now actually it's probably about 30 nanoseconds. You should be able to find the latest performance number on the EMP repo, because that one will be most up to date. Okay, so before I talk about exactly how it works, let me give some intuition how we think about it, how we can actually come up with this kind of protocol. Okay, as I said early on, this kind of information theoretic message authentication code was originally designed in the context of maliciously secure multi-party computation. Okay, and after we finished this work on ferret, we were thinking, okay, so now that we have this, what are the useful where it can be useful? Okay, and then we think about, okay, so so this was traditionally used in secure multi-party computation. Maybe we can think about whether there's any kind of relationship with zero knowledge. So why we want to think about zero knowledge? Because zero knowledge is literally just a secure two-party computation, maliciously secure two-party computation protocol where one party does not have input. That's it. If we think about how it does not really any. I mean, at least from a MPC people like me, it's literally just a MPC protocol where one party does not have the input. Okay, so what we do is that we take the most classical maliciously secure two-party computation protocol, one of them, which is tiny OT, published in Crypto 2012. Okay, so we took that paper and and then next step is like, okay, so now that only one party has the input, let's just try to shave off the part of the protocol that doesn't really need to be there because just one party has the input. And then with further optimization, that's how we get the Wolverine protocol in the next slides. So actually, the idea is not very. It's just a very easy, simple idea. Okay. With that, now we can think about. Let me describe exactly how it works. Okay. So in the first step, we are going to do some kind of preprocessing to compute some kind of like a bunch of random authentication of random values. So totally, we compute the C plus n number of them. And so the n is the input size of the circuit, and C is the circuit size. And for prover has a input has an input vector from omega1 to omega n. So the first step is that so what we want to do is that we want to kind of follow this kind of gate by gate paradigm, and let the verifier to be able to hold authentication of all the circuit wires in the circuit. Okay. So if two parties hold a random authentication, and we prover wants the verifier to hold the authentication of the input value, that's kind of easy. We just need the prover to send the difference of the random value and prover's own input, and then they can just do some kind of local computation to fix it. So this is the first step. So a prover can just send one message containing all different kind of differences to the verifier, such that they hold the authentication of the input. Okay, so now we just we have the input authenticated. We just want all the wires in the circuit authenticated. And in order to do this, we are going to compute it gate by gate. So we really just need to think about for the gate how to do them, for each gate how to do the computation. And because the information theoretic MAC is already additive homomorphic, the addition gate is easy. Okay, so whenever they meet a addition gate, they can just compute the authentication of the output directly. That's easy. And then for the multiplication gate, that's always the difficult part. That's also the case in the two-party computation. Okay, so what we do is that so it's not really clear how to do it, but it's fine. We are going to let the prover, we are going to trust the prover for now, and ask the prover to send to kind of help the verifier to get the commitment of the multiplication of the input wires. So this could be done by just letting the prover send the difference of the true multiplication and the difference of the multiplication and the random value. Okay. So in the previous one, for the input, we send the difference between the input value and the random mask. But now we just send the difference between the multiplication and the random mask. So it's literally just the same thing. Okay. And now the prover and the verifier hold the. I mean, if the prover is honest, then two parties hold the the authentication of the output wires for the multiplication gate. Okay. So far so good. So so after this step is done, the two parties are going to hold have authentication of all the wires in the circuit in their hand. And at this moment, the prover cannot. There's not really any way for the prover to change any value because everything is authenticated. Okay. So the next step is to do this kind of consistency check. Okay. So essentially, if we look back, so the only place that the prover can cheat is to send a different value for the difference for the multiplication gate, because everything else doesn't really there's not really any chance for the prover to cheat. So we really literally just wanted to cheat to check that the prover actually does this part correctly. Okay. And the way that to do it is so this becomes actually a very classical problem in secure multi-party computation. This is how to do the consistency checks of triples, because if we look at all the multiplication gate in the circuit, we have the authentication of input wires and output wires of all the gates, and we want to check that all of them are correct. Okay, so the most classical way to do it, which is what we did as a simplification of the tiny OT paper, is to using using some kind of bucketing to kind of first generate the same number of correct triples, and then we can use the correct triple to check against the incorrect triple. So I'm not going to go into the detail exactly how it can be done, but believe me, it's just a simple a cut and choose kind of game. And to do this, so roughly in order to check one triples, we need roughly 3 triples when the number of gates is more than 1 million. The major overhead of this kind of protocol is in this kind of cut and bucketing. We needed to do this kind of bucketing and repeat a lot of times in terms of the generation of this kind of random triples. So this is the most heaviest part of the protocol. Okay, and obviously this is not the best that we can do. We can definitely do better, because this kind of idea is more or less like a direct transportation from the two-party setting, the multi-party computation setting, to the zero-knowledge proof. Okay, so how to do better? So in order to do better, so our idea is to look into the information theoretic max. Okay, so in the previous message, in the previous protocol, right. So in the previous protocol, we only look at this kind of authentication as a black box. Okay, so the protocol would work even if this kind of authentication is done by, for example, some kind of linearly homomorphic commitment scheme. So that would also work. Okay, but maybe that's maybe if we want to get better efficiency, let's go actually inside of this kind of information theoretic map, and that's what we did in the Quicksilver check, in the first part of the Quicksilver check. Okay, so essentially, let's think about it that we have a multiplication gate. Okay, so once we have a multiplication gate, the two parties want to check that the output wires equals to the multiplication of the values on the input wires. And at the same time, we also know that all the authentications are valid, which means that we have this kind of relationship. Okay, so so I changed the addition to subtraction, but it doesn't really matter, because the sign doesn't really matter that much. Okay, over here. So essentially, we just wanted to check that all this four relationship holds for every gate. Okay, so now let's just think about it. What does it imply? If all of them are true. Okay. So what we can so let's think about what verifier can compute on the first. Okay, so the verifier can compute what we have on the left hand side. Okay, so verifier has all the keys, so which means we have the key for each of the wires and also the global key. So this is something that the verifier can compute. Okay, on the other hand, let's try to expand this into something that probably the prover could compute. Okay, so if we expand it, let me see whether I have. Okay. If we expand it, maybe I can draw it. Okay. So Ka is going to become m of I plus omega I times delta, because we have this relationship. Okay. So this means that this whole the left hand side is going to equal to this where the subscript is alpha times the same thing with beta minus the same thing with gamma times delta. So it's going to be m plus omega alpha times delta, and then times m beta plus omega beta times delta minus blah 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 times delta. Okay, and so we have two terms here, and two terms here. So when we expand it, it's going to give us 6 terms, right? So the first term is the multiplication of this term and this term, and this is the cross product term between these two and this two, and one of the term is here. So these are the terms where the degree of delta is 1. And finally, there's also a degree degree 2, a delta 2 degree term, which is the multiplication of this and this and this. So multiplication of these two minus these two. Okay, so this is going to give us the last term. Okay, so it doesn't really seem to to go anywhere, because so what? So we know that this relationship should hold, but it doesn't really give us any hint. Well, so not really. This actually contains a lot of information, and in particular, so we know that okay, so this value is known by the prover. This value is also known by the prover, and this delta is known by a verifier, and this term is actually not supposed to be there, because we know if the multiplication gate is really a multiplication, then this coefficient is going to be 0. Okay, so if the multiplication is correct, then this is 0, and if multiplication is incorrect, then this becomes a real term. Okay, so so in another word, it means that if we wanted to check the correctness of this gate, we just wanted to check whether this value, and this value is a linear relationship, because if the gate is correct, then this term doesn't appear anymore. So then the rest part should be a linear relationship. So we convert the checking of a multiplication which is kind of a degree 2 kind of relationship, into a linear relationship. So we go from like a degree 2 checking to degree 1 checking. Okay, and the degree 1 checking is easy because, like for example, we can just we can first like obtain a random linear, like a linear triple, satisfy this relationship, and then just use one to check against the other one. So the linear checking is easy. So like this is one of the example where we can, like, if we have this is kind of similar to the the previous cut and bucketing, like a kind of checking. So if we have a good one, it's very, very easy to use this to check the other one. Okay, how to do the, okay. So now, but this is not like good enough. Why is that? Because like so for every gate we needed to come up with a linear triple to check it. Then we still needed to use like a lot of communication to do the checking. But don't worry. So why is that? Because like let's say if we have many gates, then it just means that we have many linear relationships to check. Okay, so we have many relationships, and we want to check whether all of them are linear. So that's also easy because like if many relationships are linear, then any linear combination of them is still a linear relationship. Okay, so if any of them is a non-linear relationship, then the linear combination of them is not going to be linear with high probability. So essentially, we can kind of squash all the linear checking, each for one gate, into just one checking using just linear combination, which is like a very cheap operation. Okay, and after that, we just need to do like a one checking at the end for the whole circuit. Okay, so this is the kind of the high-level idea how we do the kind of this kind of a Quicksilver checking. So the overhead, the communication overhead of this checking is essentially big O1 for the whole circuit. Okay. Let me quickly go through the performance. For example, for the Wolverine protocol, at 1 megabyte, 1 megabit communication, it requires roughly like 460 nanosecond per gate. And with the improved Quicksilver protocol, actually this can be like this is much quicker. It's like roughly like 100 nanosecond per gate. And this is like I think it's even faster now, like in the latest code, because we did some follow-up optimization. Okay. So actually, like so in terms of the affordability, we are thinking of, okay, so like now the protocol is actually very cheap because it does not really need any kind of heavy operation, and it's also very memory efficient. So we take the weakest instance on Amazon that doesn't really has any kind of fluctuation in the CPU, and then we benchmark their performance, like in this case. And even in this case, like the speed is not as high as before, but it's still like decent. It's like a 5 million gate per second, even using a medium like ARM CPU. And with that, like the cost is about, we can compute about like 10 billion gate per US cent. Well, like at that time, because like there's some inflation since then. Okay. So if we calculate convert the cost in terms of where the unit is, let's say like a Starbucks coffee, then like one cup of coffee, like the worth of one cup of coffee would allow us to compute a 365,090 number of AND gate. So it's pretty much like pretty much whatever you want to compute can probably be covered by just one cup of coffee. Okay. We have so we actually can also do like a matrix multiplication is faster. And over here, like we compared with, for example, like interactive protocols and interactive protocols and non-interactive protocols. Okay, and you can see that actually because our protocol is interactive, actually the communication is much higher than prior work, and the execution time is similar in the circuit model. Okay, and there's a last line where it's called polynomial, and it's so much smaller in terms of the communication and also the execution time. And this is some this is some further improvement on top of the protocol that I just mentioned in terms of the circuit model. Okay, so the high level, this is kind of related to what I just mentioned at the very beginning of the talk when I say often linear size ZK. Okay, so why it says often, not always, because there's some kind of improvement that we can do on top of it. And this kind of improvement actually also appears in for example, in the crypto paper on fully linear PCP by Bernay et al. Okay, so essentially, if part of the a circuit can be viewed as low degree polynomials, then actually the computation of the polynomial is essentially I shouldn't say computation, the verification of the polynomial is almost free in terms of the communication and the computation. Okay, So I probably I don't have time to go into exact detail how it works, but essentially, for example, so this is what we just mentioned in terms of a one multiplication. Okay, so essentially the same idea can be directly applied to the inner product, and the computation still works. So essentially, so in the previously when we do the multiplication check, I was saying that okay, so we can convert a degree 2 computation of multiplication into a degree 1 checking by asserting that the last term doesn't exist. Okay, so actually because inner product is also just a degree 2 computation. It just has more terms, but it's still a degree 2 computation. So actually there's a way to directly translate this into the setting of inner product. Okay, so actually it can be translated into any degree 2 computation is in a similar way. So essentially, if we want to check degree n, we just so any degree n computation can be converted into a degree n minus 1 checking. And because of the the random linear combination technique, regardless of how many degree n computation, they can always be squashed into just one of them. So in the end, what it really matters is just how many different kind of degrees of polynomial that is needed in the whole computation. Okay. Yeah, so this part I probably will just skip it. This is just how it would work when the degree of the polynomial is higher. So it requires a little bit more effort because usually the ways that a polynomial is represented is not really friendly to be used. So we actually need to kind of change it a little bit to be applicable for higher degree. And it just so happens that for degree 1, it just for degree 2, inner product and multiplication, it just doesn't have this kind of a hazard. Okay. And one of the example how it would work is that, for example, let's say this is just part of the circuit, and for this part of the sub-circuit we have 5 input wires. Okay, and then the whole circuit consists of 3 computation of the polynomial. Okay, so the first polynomial takes take these variables and compute this polynomial where the highest degree is 5, and actually all of them has highest degree as 5, and in the end we output 3 values by using our improved protocol. So the total cost would be linear to the input size, which is 5, and output size, which is 3, and also the highest degree of all the polynomials, which is 5. So the total communication complexity of the protocol would be 5 plus 3 plus 5. Although there are so many different kind of multiplications inside of it, they can be done in some kind of local way easily. Okay. So I quickly go through some circuit-based zero knowledge because I want to talk about some more exciting stuff. What can we build on top of it? Okay. So the first example that I want to give is about is kind of connected to machine learning. Okay. So nowadays there are so many so one popular attacks that people can do on top of models is so-called evasion attack. So in this kind of evasion attack, it's if I add a small noise on top of the data, then the model is going to recognize the input as something else that is completely different. Okay, and this kind of attack can always be kind of very bothering if the model is used in some kind of a critical infrastructure. Okay, so in some sense, it's kind of similar to what happens with code. Okay, so nowadays many companies, they have this kind of code a bug bounty kind of program where, let's say, if a white hat hacker can find a bug of the code, we can submit it to the company, and the company will say, okay, so this is a good bug. You helped us. I'm going to give you some money. Okay, so maybe in the future it's going to happen for machine learning models as well. So let's say if I can find a bug, which is the evasion attack of your model, I can let you know, and you can kind of give you can kind of reward us in some way. Okay, but however, in this case, maybe I don't really want to let you know, because if I let you know, maybe it's okay. So you can choose not to give me the money. So in this case, so we are kind of in a dilemma, because the developer who develops the model is only willing to give the reward if the challenger can actually show a evasion attack. Okay, but on the other hand, the challenger does not really want to kind of show how this evasion attack looks like unless the developer actually give you challenger the reward. Okay, so in this case, actually we can use a zero-knowledge proof to prove the existence of the knowledge of this kind of evasion attack without really telling the other party exactly how this kind of attack works. And after this, after the developer is convinced, then they can continue to the next step. Okay. Okay. So so in order to build this kind of like a complicated like application like a zero-knowledge proof inference, we actually had like a few more examples how like this kind of zero-knowledge inference can be used. But I mean, like I just want to mention like this particular one. Okay. So we actually it's like actually involves like multiple like components. Okay. So this part is pretty much like a kind of standard for every machine learning like related application. Okay, so mainly there are like three parts. Okay, so like there are linear part, which is just convolution, or you can view it as matrix multiplication with a little bit loss. And the other part is just the nonlinear layer. Okay, so the nonlinear layer could be, for example, like all different kind of computations on top of the on top of the like arithmetic circuit. And then there will be some like some kind of authentication of the input and output, because we don't just want to compute. We don't just want to verify a computation of the inference. We also want to do something on top of it. For example, like for the evasion attack, we might want to say that okay, so it has a correct inference, and the input is different from a normal picture with certain like distance. So like this is kind of a composition of different statements. One part of it is about machine learning algorithm. The other part is about something else about the constraint. So we really want the input and output to be authenticated. Okay. And once so what we need is really just like build efficient building blocks for each part, and this really has to be efficient because all these models are really complicated. For example, for a ResNet like a model, for a reasonable ResNet model like a ResNet 100, 101, it actually has like 3 times 10 to the power 7 number of parameters. Okay, so that's like a lot. And like once we have like if we can build this kind of protocols, then like the prover can essentially just use the private this kind of like a small like a population as the witness, and then prove to the developer that see I can actually like add some noise to the expander, and then it becomes a gibbon, which is like some kind of monkey. Okay. So the most difficult part in terms of designing this kind of zero-knowledge proofs is the conversion between the linear layer and the nonlinear layer. Okay, because like for the nonlinear layer, it could just be done in Boolean circuit, because many of the linear layers are like just floating point operations, and we do not want to really like lose any of the precision. So we actually preserve the floating point computation like as it is. So actually we literally verify the floating point computation. Okay, but on the linear layers, in order to make the linear layer efficient, we actually compute them in in prime field, like FP with some large prime. Okay, so this conversion between the arithmetic and the Boolean is actually the most is the bottleneck in the whole computation, because the linear layer is actually there are actually many different kind of tricks to improve it. In particular, for example, if we just want to verify the multiplication matrix multiplication, it can actually be done in sublinear cost. Why is that? We can just come there's this famous trick. I can't remember the name. The name is not very easy to pronounce. It's like if the multiplication is correct for two matrix, like any random linear combination of the matrix is also it should also be correct. So you just need to check for a certain number of random linear combinations. Okay, and then it's really just about this kind of conversion. Okay, and this kind of conversion again, we look for an NPC for help, okay, because we've already there has been many great researchers listed below that have already done this kind of conversion in some way in the multi-party setting, okay. And for example, one of the most efficient way to do it is so-called called ADA bit, extended doubly authenticated bit. Okay, so you can from the name you can see, okay, so it is deeply rooted with authentication, because it's like the postfix is authenticated bit. Where is my mouse? Okay, yeah. So for us, so essentially what we do is that so if in the multi-party setting we want some kind of extended ADA bit, then maybe in the zero-knowledge setting we should have some kind of zero-knowledge ADA bit. Okay, and that's actually what we did. Okay, and and over here there's so essentially what we need to do is that we can let the prover commit a lot of different kind of hopefully correct authenticated triples where like the value itself and also the bit decomposition of the value are all committed, one in Boolean and one in like the arithmetic field. And then we just need to do some kind of a probabilistic check to check that actually many of them are indeed correct, and then try to kind of play around with it. Okay. However, because that the field is different, one is F2 and one is FP, it's not clear how to use the efficient Quicksilver like a non-black box checking to check the consistency. And what we did is that we just use the like a traditional like a cut and choose of the ways to kind of check the correctness. However, like the performance is actually still like a good. Like I wouldn't say like as good as like the circuit, the computation of the circuit zero knowledge, but it's still something reasonable. So for example, for one conversion, it's like 30 microsecond. That's like this means that we can do about 300 or 300K triples per second, 300K or yes, sorry, it's like 30K triples per second, and that's actually roughly like sufficient for our application. And this is like one of the the most interesting figure that I want to talk about. So essentially, so this is what we observed when we run our protocol on private model and public model. Okay, so the witness, which is like the input, is always we use that as like the private witness, but we could make the model public or private. Okay, so and obviously like in the case of where the model is private, the computation is going to be much higher. The reason is that now many parts has to be done inside of zero knowledge rather than just like plain text computation or like some kind of a constant computation that can be done cheaply. And we can actually like a large proportion of all the time is done by on top of like a batch normalization. Okay, so this part is like there mostly because we just wanted to take the off-the-shelf parameters from, for example, TensorFlow. Because like this part is really just computation of the parameters, like a model parameters, and there's nothing to do with like the witness. So let's say, so in this means that actually, if we are willing to use some kind of customized model, we can actually pre-compute this part of the cost and push it to as part of the model. So in that case, that actually the running time is going to be just like the rest part of the timing. Okay. And then regardless of that, actually just like one inference of ResNet 101 actually just takes about 500 seconds. So like this is actually very, very, very efficient compared to what we could do for like, for example, two-party computation of the ResNet network. So zero knowledge is actually much faster. But it's kind of unfair comparison because like a two-party computation is like a more difficult task anyway. Okay. Okay, so like so we can do like a inference, and there's still a lot that we can do. For example, in terms of how to design like the model so that it is easier to check, and how to actually check it more efficiently. Okay, but at least now we show that okay, so this could actually the inference could be proven like in reasonable amount of time, and also using like a reasonable amount of like a hardware. So for this number, actually we just use a very like a mediocre kind of server with, for example, like I think like something like 8 GB of memory or 16 GB of memory is just sufficient to prove this, and it contains like hundreds of billions of gates inside of if we actually represent it as a circuit. And more general comes to the REM model of computation. Okay, so many like computations that we want to prove inside of zero knowledge are not really friendly to be represented as a circuit. For example, like one of the examples that we have in our paper is like memory hard hash function. Okay, proving the pre-image of a hash function is kind of a very classical example that we always talk about in zero knowledge. Okay, and the memory hard hash function is probably the most difficult one because like a memory hard hash function contains a lot of random access in like during the evaluation of the hash function. Okay, and for that, let's say if you want to do that, we literally need a way to do random access more efficiently. Okay, and so this is kind of the high level picture of what we need to do. Okay, so I'm going to get back to this picture afterwards. Yes. Okay. Yeah. Okay, let me first go to the intuition. Okay, So essentially, let's think about it. Also, what do we need? Okay, so we really just need a kind of a structure that allows us to initialize, allows us to do read and write, and allows us to check whether everything is good for for all the accesses. Okay, so if we have some kind of like a structure for this, then we can actually compose it in many different kind of ways. For example, we can build a arbitrary, like generic RAM computation that that is similar to, for example, like a CPU, or we can build like a application, like a tailored implementations. Okay, so we really just want some kind of structure that can help us to do this. Okay, I mean, like initialization is pretty simple because we can let's say if the parties has already the content authenticated, we can, for example, we can just store all the content as a list of authenticated values. Okay, and so following up to the philosophy that in terms of how we design it in the Quicksilver and Wolverine, like for read, we can, and for the access, we can always just ask the prover to provide the authentication as the promised value, and then we can handle with the correctness afterwards. And then it's really just about the correctness, the checking. Okay, so this kind of checking in the read-only sense is simpler. Okay, so what do? We really just want to do 3 tasks. Okay, so the first part is that we wanted to sort all the accesses by the address. Okay, so why is that? Because essentially for read-only, the content is not going to change. So we just want to check that for all access to 1, they are all the same to 1. For all access to 2, they are all the same to 2, and so on and so on. So the first step would be rearranging all the access such that all the 1s are gathered together, all the 2s are gathered together, and so on and so on. And then the second step would be a simple check to check that everything is correct, everything is consistent. So this part would be if the index is same, and if the indexes are the same, then the value that is being read out should also be the same. And otherwise, it should just be monotonically increasing to the next index. And this can be represented as a circuit, as a very small circuit, because it's literally just linear to the bits of the index and the payload size. And the last part is to it's kind of related to 1, is that we want to check that the sorted list, the list before sorting and after sorting is the same. Okay, and checking that the list before and after is we essentially just want to check that 1 is a permutation of the other. And this is again, if we want to do it in circuit, then we would need at least n log n cost. For example, using some kind of permutation network. Okay, but we don't want to do that because we are doing zero knowledge. This means that there's much more things that we can do, in particular in terms of non-determinism. Okay, so what we do is that okay, so we are going to checking permutation is just about the checking set. Okay, and there are many different ways of encoding set, and one of the most crypto-friendly way of encoding set is to use polynomials. Okay, so we can convert the checking of 2 sets to checking of the 2 polynomials, and then we like it because checking polynomials is easy. We can check the equality of the 2 polynomials by using Schwartz-Staple lemma, and then we just need to check a particular point, random point on the polynomial, as long as the field size is sufficiently large. Okay, so that's so this is also being used a lot in for example, honest majority MPC when we check the correctness of the computation and many other different kind of places. So the checking by using Schwartz-Staple is is not a new idea at all. It's being used for so many times already. Okay. However, one part that is kind of a little bit annoying, that is often being ignored, is that over here when we do polynomial checking, I think I'm almost out of time. Okay, so but let me give you a little bit of high-level idea. Okay, so for the polynomial checking, to invoke Schwartz-Staple lemma, the key is that the field size has to be large enough, because the soundness of the checking is kind of inverse proportional to the size of the field. Okay. However, when we do the first part, this is in Boolean. So this is in Boolean circuit. So in some sense, again, we need some kind of conversion from Boolean to a field, from F2 to some kind of larger field. Okay. If we use of course we could use the Boolean to arithmetic computation that I just conversion that I just mentioned in the context of machine learning, but that's not really the best way to do it, because that's like the cost of that is pretty high. Okay. But we have a little bit more freedom over here, because now we can choose any field of our choice. Okay, so we can choose whatever field, and that field doesn't need to be very intuitive. Okay, and in particular, like in this case, actually, we can use another property of the information theoretic MAC. Okay, so essentially, this kind of property is that not only we can do addition and addition by constant and multiplication by constant or locally, we can also do actually like the conversion between base field and the extension field locally. Okay, so essentially there's a very simple way of lifting the base field F2 element to the extension binary extension field F sub 2 to the K easily using just like a local computation. So this means that actually we can actually do the conversion, field conversion like for free, essentially for free, with just like a cheap operation locally. Okay, so this is actually one of the most important part that enables information theoretic MAC-based zero-knowledge proof to be very, very efficient for RAM computation. Okay. Yes, I promise to come back to this. That's like where I want to talk about when I say conversion over here. Okay, and of course, like for the checking of the polynomials, this could actually can be further improved by using Quicksilver, and which is actually what we did in our paper. And finally, we get back to the like performance. So this is like the x-axis is like the size of the RAM, ranging from 32 elements in the RAM up to 1 million elements in the RAM. Okay, and the access time for each of them is like the per access time time for each of the operation. For example, like even for like a 25 megabit of network, like each access. Zero knowledge proof of random access takes about like 20 like a microsecond, which is like pretty nice. Okay, and in terms of the communication, we are also like at least an order of magnitude better than the prior work. Okay, so this bubble cache actually leaks some timing information. This is actually an improvement by leaking some timing timing information about the access. But the author actually had a recent work that actually get some performance similar to this, but it doesn't have the like leakage anymore. Okay. Yeah. Yes. Okay. So that's all I want to talk about today. So it contains a lot of work, and I tried to be able to pack like all different kind of ideas together. So all the papers are online, obviously, and the code actually majority part of the code is also already like released online. And there are like quite a lot of people already started using it in different kind of settings. So if we are interested in trying it out, you can go to EMP. You can search for EMP toolkit in Google, and you should be able to find all the code. Okay, and thank you. I'm happy to take any question.
Yeah, thank you very much, Xiao, for a very interesting talk. Any questions from the audience? I have a couple of questions, but maybe we can start with the others. Anyone have any questions?
Maybe I'll ask a quick one.
Yeah, go ahead.
So I was actually planning to ask the question about the code because we use your library a lot.
Oh, really? Okay.
Yeah.
FlexX,
okay, starting from FlexSA and later we are using EMP toolkit. Yeah, because I'm doing research on like applied secure computation in different applications, and also we tried different kinds of MPC libraries, and we find that your library is the most easy the one to use.
Oh, thank you.
It's actually very well written, and also but my question is not very related to the technical part. It's more related to the application scenario part, because you mentioned that you have a motivation for ZKP to apply to the machine learning, right? So which you use like example of to trying to mitigate the evasion attacks, right? So
it's not. It's not really mitigate. We cannot mitigate the evasion attack.
Okay. Yeah. So that's my question, because I'm wondering, because for the evasion, it's like it's some kind of, it's not called vulnerability. It's kind of like inherent properties of the machine learning model, right? So because you generate a adversary sample so that you can bypass the classification. So that's why I'm just wondering whether ZKP can indeed, solve this. Probably it's not. But you mentioned something like, okay, there may be some like software bugs, right? So it's more like you have some model deployed or designed at the developer side, and the developer validate the model, right, at the local side. But later, if the developer deploy it in the cloud, right, so there may be some changes or maybe some bugs on the service, machine learning service platforms. So this is probably some scenario you want to target, right, to address, so that the original, the output or the input is different from the one when you deploy it in the outsourced environment. Is that correct?
I'm not sure I get I think I lost the first part of the question, but maybe we can continue this part of the discussion offline. I feel it seems like a very complicated and a little bit philosophical question. Maybe we should discuss it.
Sure. No problem. Yeah. So it's more like application scenario on the ZKP, because recently we also submit a paper to Big Four and regarding this verification, but it's not using crypto approach, it's using learning-based approach. So then one of the reviewer asking okay, whether this is realistic in the outsourced environment, why the cloud provider they have to behave malicious. So this is one of the concern raised by the reviewer. So that's why I just want to see, maybe in your opinion, so what is because if you say, okay, the ZKP can solve to address some malicious attackers, so what is exactly the practical scenario so we aim to target? Yeah, but later we can definitely discuss it offline. Yeah.
Oh, and so in terms of the code, the good news is that if we want to switch, let's say if you have some circuit written for some application, switching to ZeroKnowledge is very easy, because the set of interface is the same.
Yeah.
And in terms of so over here we are not really talking about outsourced computation at all. So we only have two-party prover and verifier, and so in some sense both party has to do the work that is linear to the size of the circuit. It's not like anybody can do less work by running the protocol. So it's more about the fact that I'm kind of telling you the existence of some valuable information without letting you know the information.
Sure.
Let's say in the case of a bug, it's I want to kind of prove to you that I have a bug, but I don't really want to tell you the bug, because if I tell you the bug, then you know the bug. Maybe that is a valuable information I don't want to give it to you. But I still want to convince to you that I have the bug.
Okay.
So it's convincing you at the same time, not revealing the information.
Okay. Thank you so much.
It's not really applicable for outsourced computation, at least for our scheme.
Okay. Thanks.
Yeah, I might also just ask a quick question. So with all these protocols, we are in the designated verifier setting, right?
Yes. Interactive. And it
interactive and designated
interactive. Yeah.
Okay. Do we have any other questions? Otherwise, I might have one last question. Anyone has any question? Okay, so I'll just ask mine. We actually welcomed Karsten Baum, who talked about this mac and cheese and so on. I was just wondering, what is because your protocols are mac and cheese, and their protocols seem very similar. And I was wondering what's the kind of the main technical novelty that enables you to do much faster computation.
So we put out. So I think so mostly we are good friends, and we have been working on MPC independently on different sides of the world for a long time, and it's not surprising that we come up with similar ideas. and it's actually concurrent. We put the paper on ePrint. I don't know, I can't remember, June or something last year. I think so I read the mac and cheese also. So I think their approach is to treat the information theoretic mac as a black box. Mm-hmm. So actually the protocol would work even if we change it to linearly homomorphic commitment. Mm-hmm. However, this is actually a kind of a big constraint in terms of what are the tricks that you can play with. Mm-hmm. And then they on top of it, what they apply is a fully linear PCP, kind of check. and then that would need like some computation on top of it. And for us, it's a non-black box way of using the information theoretic maps. So we look into inside how the map is constructed. And that actually gives us a lot of advantage in terms of, for example, being able to actually check faster and also being able to check even polynomials altogether, like as a whole.
Okay, yeah, that makes sense. All right, so thank you very much, everyone, for tuning in. And thank you, Xiao, for your very interesting talk. It's really nice to see that ZKP and all this, like, let's say, privacy-oriented stuff is taking a big leap, and hopefully it continues this way. So thank you, everyone, again, and hope to see you in the next talk.
Thank you.